In this lecture, we will derive the Joule's law of heating from very basic equations. Now, we know that whenever there is a current flow in a conductor, then there is a drift motion in the electrons. Now, these electrons, while moving, will collide with the atoms on the which are present on the lattice sides of this conductor. So the electrons which have gained some energy because of the electric field, they will now transfer some energy to the lattice atoms, and they will in turn will cause the loss of energy in terms of heat or the increase in temperature of the lattice, or the thermal vibrations will increase. So we want to derive some equation for that effect. Now let us say that there is this charge Q which is moving in electric field E. So this electric field E will do some work. Let us say this work is delta W if this charge is moved by a distance delta L, and this delta W is now thus given as QE dot delta L. So this is the small work done by the electric field on the charge. Now the power is simply delta W over delta T is equal to P is equal to QE delta L over delta T. Now, in a limit, when this delta T tends to 0, then we are going to have the power is equal to QE dot U, where U is now the average drift velocity of the charge in the uh, conductor. And we have already seen something about the drift velocity in our previous lectures. Now let us say there are n charge carriers per unit volume of the conductor. So the total power delivered to all the charge carriers in a given volume dV can be written as dP is equal to the summation of all those small pi's over all the charge carriers is equal to field E and summation of over all the charge carriers. So this is the n charges per unit volume, and this is the volume. So this is the number of charges into charge on each type. So let us say there are various kinds of charges: electrons, holes, or ions. So I will sum for all into U I for all charges. Now, in our previous lecture, one of the previous lectures, we have seen that this quantity NQI UI is simply the electric current density. So this dP is simply E dot J dV, or the power density, that is power dissipated per unit volume or power consumed or transferred from the field to the lattice per unit volume, is given as E dot J. So if I integrate, then I can find the total power transferred from the field to the lattice, E dot J dV, where this is now over the whole volume of the conductor. Now, if the conductor has a constant cross section, so dV can be simply written as the cross section ds into dl, where dl is now measured in the direction of the current density J. Okay, so this power is simply now written as E dot J ds dl. Now continuing in the next slide. So P, now I will club these two. E dl dot dl, of course, J ds. So I am assuming that the directions are such that this dl is in the direction of j, and this ds is uniform everywhere. So these dot products or the vector signs will not matter more. Only magnitudes will do the job. So I can write it as E dl j ds over the surface. This is the volume integral. Now this is a surface integral and this is a line integral. So now EDL is simply the voltage across the points, two endpoints of the conductor, and this is the current through the conductor, or I can write it as I square R. So this is the simple I square R law of heating in a resistive conductor or in a resistance. So in this way we have derived it from the first principles from the theory of electromagnetism. So you see that this is an equation which is very familiar to us, and it represents the ohmic power or the heat dissipated in resistance R per unit time. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel and join our Telegram group, whose link is given in the description of this video. Thank you.